Super happy to be here. Um, so yeah, I have a bunch of slides, potentially some Jupyter notebooks, but for now the plan is really to kind of go through at least the basics, explain what's going on, and I'll try to get a feel for how people are doing. If you want to do more code, try to assess that. But in the spirit of this being a tutorial, the point is really for you to like understand what's going on. So like, please ask questions. Um, Raise your hand. We can go on tangents. That's totally fine. Again, I have a bunch of slides. We don't have to go through them in order. I can jump around. If there's some topics that interest you more, I'm sure we can have interesting discussions. Um, so yeah, that's the plan. Um, let's get started, I guess. Cool. Yeah. So the actual plan of the current set of slides. So I'll start by kind of giving the motivation why we came up with this framework, GFlowNet, what it is, what's the intuition behind, what are the objectives that it leads to, training methods. I'll then go through some more, let's say, advanced. Does this work? Yes. Advanced training methods that we came up with. So I'll talk a bit about continuous GFlowNets. I'll then make parallels between GFlowNets and other generative frameworks, talk about some kind of real world applications. And then by the end, I'll get more meta and talk about things that we could be working on, that we should be working on, and especially how I'm hoping that GFlowNets enable things like scientific discovery. So, what's a GFlowNet? First of all, what it is not. It's not a neural network architecture, even though the name has net in it. Sorry, we didn't think too hard about the naming. But it's also not a normalizing flow, even though there's no name flow in it. Flow comes from the really cool metaphor that we use to try to understand the maths. So what it is, it's a generative framework. We designed it to sample combinatorial objects that can also include continuous things like parameters, but also structures like molecules, Bayesian networks, language. And we designed it around the idea of diversity, right? So it's an energy-based model. If you have an energy function or reward function, you can try to match that in a proportional way rather than like an optimization, find the best thing kind of way. It came about basically because of COVID. So I was a deep reinforcement learning person during my PhD. And then because of COVID, a lot of projects started at Mila that would try to contribute to maybe making a dent. And one of them was, hey, let's try to do drug discovery. Let's try to design small molecules that bind to the COVID spike protein. Maybe that's helpful. We don't know. And the problem was extremely hard. Of course, the best we had was this like super noisy physics simulator that gave us a reward. It was extremely slow on CPU. It was also extremely noisy, right? Which meant that we had a whole bunch of candidates that looked good. We didn't know exactly what that meant, but they were also rare, right? So needles in a haystack. You have a huge state space, and this basically the space of all molecules in this case. And they all look very different. Like the molecules that actually bind might look very different. And then we have to send what we think are the best to a simulator, maybe a wet lab. Base question, what do you send? How do you find these things? And we wanted the answer to be, let's be as diverse as possible. Let's not bet on the same subspace everywhere. And the answer to that was, let's be as diverse as possible, right? Again, you don't know exactly what's going on, and there's a whole lot of unknown unknowns, right? Here again, with the example of organic chemistry, all the proxies that we use, be it molecular dynamics, ABFE, docking is even worse, right? They're fundamentally imprecise because we can't really simulate reality 100%. We can't simulate cells very well, can't simulate brains very well if you're there in the early tutorial, but we can try. And that means that we're going to get some answers from our models, but they might not be truthful or reliable. And so to get the best out of our wet lab experiments, we really want to cast a wide net. And that's what's pictured in this little cartoon here, right? If your model of reality is predicting that there's 4 of these high reward modes in your state space, you'd rather try, if you have 4 tries, you'd rather try like 4 things in 4 different modes rather than 4 things in one potentially incorrect mode. Another reason why diversity is good is, well, this is my deep learning background showing, obviously, but diversity is good for generalization. We know this from theory, we know this from practice with neural networks. You want your data, the data in which you train your model, to span as much as the space as possible, especially and ideally in a kind of combinatorial way. And something that is a peculiar, say, feature of GFlowNets, but similar to many other frameworks, is that if you're using the right function approximation, your model will have this self-induced data distribution. And I'll get back to this a bit later. GFlowNets will kind of naturally try to probe at the entire state space by leveraging as much as possible the generalization of the model that is underlying the generative model that you're trying to fit to the energy function that you have or the reward function that you have. And so this is going to be fundamentally good for systematic generalization, right? You'd hope that there's this kind of self-induced bootstrapped effect of, hey, I'm seeing diverse data, therefore I'll be better able to acquire diverse data, and that will naturally help your model generalize better and predict better where there might be reward. So yeah, hopefully the motivation is fairly clear. Again, this is meant to be as interactive as possible, so please raise your hand at any moment if you have questions. So the traditional way to solve this problem is basically 3 categories. The first is reinforcement learning. For molecules in particular, we have actions, right? Plugged to atoms or plugged to fragments together, rewards, whatever simulator you're using. And then the problem is exploration is really hard, and reinforcement learning works in such a way that it tends to collapse to a low diversity solution. The kind of gold standard then is MCMC, just do a bunch of Markov chains. There's a lot of tricks, right? And they work really well, really good baseline. But obviously, slow mixing, there's all sorts of problems with them. I'm sure a lot of you are familiar with these. Right? And then the third category of solution is, well, if you have a data set, just do maximum likelihood, sample, filter. That kind of works. In fact, it works extremely well for things like LLMs because we have so much data. In something like biochemistry, it might not work as well. In particular, because we have a lot of negative samples. So we have huge data sets, right? We can enumerate billions of molecule and enamine real or whatnot, but most of them are kind of useless. They don't do much. But they're still interesting. They're negative samples. We don't want to throw away that data necessarily because it is informative to the model as a realistic molecule that could exist in reality. And so, again, kind of in contrast with reinforcement learning, we don't want to maximize reward. We want an energy-based model. We want something that's proportional to the reward. So we want something that gives us the probability of a sample is proportional to reward, in fact, divided by the normalizing constant Z, but we don't want to use MCMC. So to motivate what we're going on, we're going to build smiley faces. And the idea here is that you're building an object, and notice that there's many ways to actually build that object. There's many trajectories for a given smiley face that actually lead to it. And that attribute actually matters quite a lot in terms of comparing to other things. And so, okay, you have all these paths, right? So you'd start here, and then you might have a model that decides to take this action with this probability, and then it's here, decide to take this other action, right? So you have this sequential process to build one thing. And now we're going to give rewards to the final object, right, the fully built object, and we're going to associate some flow with that. Okay, so think water through pipes. And what I'm highlighting in this little animation in particular is the flow that's associated in particular with this terminal state that has reward of 3. And you'll note that I've chosen somewhat arbitrarily to split the flow in 3 here and again in 2 here. And it kind of recombines here to be, again, associated with this particular face. Seems rendering is hard, but eventually lead up to, again, 3 near the initial state. And once we have this flow, the interesting thing we can do is say, okay, we're going to define this policy that we call PF, and it's going to be a generative policy. So it's going to tell us if we're in one particular state, how do we choose what state to sample next? Well, it's just going to be the ratio of the flow on one edge, so f of s to s prime, divided by the flow of all outgoing edges. So here the sum over children of that particular node. And that gives you some kind of categorical distribution. This extends almost trivially to the continuous case, right? You could define this PF to be any distribution over the reals or whatever your kind of next state distribution is for what you're trying to generate. And what's really cool is that if you choose this as your generative policy, well, that gives us a generative model. And in particular, it gives us a generative model where we recover the fact that we end up at any particular terminal state with probability exactly proportional to the reward. So I'm going to pause here just to make sure that this is clear. Hopefully this is like small scale enough to be accessible. No questions? Means that I explained very well. Yes, there is a question in the back.
How are the intermediate states determined? Like, how do you say, okay, this one place in the middle has... Oh, yeah. Okay, now with the microphone. No, I'm wondering how the intermediate states are determined. How do you say that, okay, this one intermediate state has a smiley face, for instance?
Yeah, there's kind of 2 answers to that. One is you choose, right? I'll get back to this maybe later in the presentation, but we're assuming here that you are in a decision process that you designed or mostly designed. Right here, I designed that the model would choose the eyebrows first and then the mouth, or second eyebrow and then the third eyebrow. Or all of them at once. Or you can get to choose what the intermediate state is.
Okay.
The second answer is maybe you don't want to do that, right? So you could technically have all the states be your intermediate space. But I'll get back to this. There's this other policy called the backward policy, where basically, I mean, I can talk about it now, right? So here, nope, went too far back. If I can pause. Yeah, so here, like I did a splitting in 3 of the flow backwards,
yeah.
But that was an arbitrary choice, and you can change that to kind of induce what distribution or what the intermediate states are going to be.
Ah, okay. All right. Thank you very much.
Yeah. Cool. So yeah, these are smiley faces. Maybe not super interesting. Is there another question? No. Okay. But yeah, in general, you might want to do something a bit harder. Molecules, for example, right? So you could imagine that you have a bunch of fragments that you are given some library, right? And you want to do a combinatorial expansion of that library. The principle is the same, right? You start with some arbitrary molecule that you kind of graft things onto. That's your action space. You can define distributions over these fragments. And you end up at the end with some finalized molecule that you may get a reward for. So, of course, in practice, if you do this, let's say for molecules, your state space might be huge. So maintaining a graph of that flow, right, the flow network, is not going to work. In practice, we never do that. We always implicitly model that flow network, right? So what you might have, for example, is some function, let's say a neural network, that has as an input the state, or maybe the state and the next state, and gives you a number. And that number represents the flow or the unnormalized flow on a specific edge, right? So I was saying earlier, there's a policy you might want to parameterize your policy to give you, one number per potential fragment, one number per potential action. That works really well, right? And once you have that, then you can train that function. So, okay, what's the first perspective? I just showed you a bunch of flows like water in pipes. So you'd like all of that to be consistent, right? You want the same amount of water that goes into those sinks, those reward states, to be equal to the flow that comes into it. And the way we express that is with this equality that just says, well, for any state S, you want all the flow that comes into the state, so the sum over parents, to be equal to the flow that comes out of the state, sum over children, and this is the flow on the edges. And in particular for terminal states, you just want all the flow that goes into these terminal states to be equal to the reward. If you find an F that satisfies all these conditions, then you are guaranteed effectively to sample from the distribution that you want, right? So if you sample from this policy PF using the strategy based on the edge flows, you get the right distribution. So now we can turn that into a loss, right? So maybe you're parameterizing the edge flows here, again, flow matching, which, sorry, important caveat, again, not flow matching in the continuous normalizing flow sense. Right, so this is the kind of first loss that we came up with. It looks a lot like TD0s, if you're familiar with reinforcement learning. You take the left-hand side of the equation, you take the right-hand side of the equation, subtract them, take the square. The problem is that that's a terrible idea. For a state space that's large enough, the flows will grow larger near S0, right? Remember, the flow kind of accumulates. The more children you have, the more descendants you have, the more total reward, the more total flow is accumulated into a particular node. So we're not going to do this in the linear space. And by the way, I don't think I've mentioned it so far, but the flow at S0 is a very special flow because it is the sum of all possible rewards, right? It is like a source node that is connected to all the sink nodes, and all the sink nodes have this particular reward. So the flow at S0 is the partition function. Cool fact for a lot of applications that you might care about. So, okay, we're not going to do this on a linear scale. Instead, we're going to do this on a log scale because things are naturally happen on a log scale. So again, you kind of do the same thing, right? You take both sides, but you take a log, and we're not going to parameterize the flow as a linear thing, instead as a log flow. We just take the log sum x here, and that's really cool. That works. That makes the learning more scale invariant. Again, because close to the terminal states, you're going to have values close to the reward, and close to the initial state, you're going to have value close to the partition function, which might get about as large as the size of your state space. Yeah, I think I'll skip those comments. Just making sure that no questions. All right. So, okay, the little problem with the parameterization I just showed you is that there's the sum over parents and children, which are a bit inconvenient, especially if you have large action spaces. You might have lots of parents, lots of children. So we're going to do a little transformation. Instead of thinking about edge flows, we're just going to model state flows instead, f of s. And recall that I said that you can define your policy PF as this ratio, this categorical distribution. Then we're just going to do that. We're going to say, okay, instead of working with these edge flows, we're going to work with these distributions. And we're also going to define a backward policy in exactly the same way. Right? So notice here that this quantity f of s is the same as the sum. So the forward allocation of the flow, right, the fraction of f of s that makes it to s prime is this probability. We're doing the same thing for the backward policy, right? Backward policy says, okay, I have many possible choices of where to send my flow backwards to define a valid flow network. Well, I can also define that as a distribution. that says if I'm given some flow at f of s prime, how much of it goes back, what fraction of it goes back to s. And this perspective allows us to then rewrite this equality just in terms of the function f of s, the flow, and the forward and backward policies. Now this is about a single transition. Instead of having this sum over all the parents and all the children, we can just write something about the transition s to s prime. And again, you can turn this equality into an objective, and this is now a detailed balanced objective, right? So if you satisfy this equation, if you drive this loss to zero for every possible pair, valid pair of s to s prime, you're guaranteed to have a flow network that satisfies the constraints that we want and which yields the right distribution at convergence. Now, the fun thing is you don't have to do that for just pairs of states. You can do that for actually any subsequence, any valid subsequence of states. Right? So you may have a trajectory that goes from Sm to Sn. You can do exactly the same thing. You write the subtrajectory balanced equation, and you start at some flow, multiply probabilities, end up somewhere. And this corresponds almost exactly to the corresponding objective, where, again, you have this log ratio. Just a note on notation here, again, we're modeling all the things on a log scale, right? So really your neural network here, f of s, might output a log flow, and your PF and your PB here might be outputting logits, right? So kind of a categorical distribution on a log scale. And yeah, you can just keep going in a way, right? There's a special type of trajectory, which is the full trajectory from S0, your initial state, to your object. And then, as I mentioned earlier, you just have that the flow at S0, well, that's just a partition function. So we're going to parameterize the partition function. And the probability of trajectory, again, it's just the flow along the trajectory. So you can just apply the same balance equation, but to entire trajectories. And the advantage of doing that is that because you're not depending on the flow estimation at intermediary points, this is kind of a minimal bias objective. It's going to be super high variance, of course. If you're familiar with policy gradient methods, for example, they're really high variance, but it's fine. Deep learning loves high variance as long as there's no bias. And yeah, it's a global objective, right? The credit assignment from I took these sequences of actions to I got a reward is direct. There's no like indirect flow estimation that's happening, except the flow estimation at the partition function. And yeah, as I mentioned, there's some close relationship with policy gradient methods that you can draw. Might cost more in memory. There are tricks, but actually we can do even better. The current like state-of-the-art objective for GFlowNets uses this trick called vargrad. And I guess I'll spare you the math. But if you're curious, you can derive this objective in two ways. Either you start from this trajectory balance equation and you apply Jensen's to say, okay, we get a lower bound on Z. And so instead of approximating the partition function explicitly with a parameter, you can approximate it in a kind of instantaneous way with a mini batch of trajectories. This mini batch of trajectories gives you actually a lower bound on the log partition function. Or this actually just corresponds to the variance of some quantity. Right? So you can say, okay, my balance equation is distributed over these trajectories. The variance of those terms should be zero because at zero loss, this is a perfect equality. So if you minimize the variance, is equal to minimizing the full thing and enforcing consistency in a kind of principle and minimally biased way because you're not actually estimating any intermediate flows. So yeah, I'm gonna stop here just to check, make eye contact. Sure there's questions. Don't be shy. All right. So, okay, I started by telling you that there's this flow network thing that you can estimate, and that if you estimate it correctly, you get a generative model, and that this generative model will sample objects in proportion to their energy. And this kind of realization yields a bunch of different loss functions that you can apply to your model to find this flow network. The thing that you will choose typically will depend on your model, on your problem, sorry. So detailed balance, right, is kind of the simplest one transition thing. It's fast, but it's kind of high variance. And then there's this cascade of spending more time per trajectory, basically, to eliminate as much bias as possible in exchange for variance. Yeah. So how do you actually train these things, right? I haven't mentioned that yet. But the default way that you would do is very much like reinforcement learning, right? So again, you start with an initial guess of the parameters of your model, and that includes this policy PF in most cases. So you just sample objects, get some trajectories, get some rewards, and you apply any of the objectives I just showed you along the states of your trajectory. You update your parameters and you repeat. And if you do this for long enough, with enough parameters, with a slow enough learning rate, you're guaranteed to converge basically to the right distribution, to the right sampler. If code speaks more to you, right, it's that simple. It's you have your model, it has an object that defines a policy, you just sample from that model, and then you compute the log probabilities of the trajectory according to PF, the trajectory according to PB, maybe your log Z if you have it, and then you just apply this loss iteratively. Right. Of course, there's lots of tricks that can be done. Unlike policy gradient methods, for example, it's easier to go off policy. Right? This means that in the training data that you give to your model, you don't have to show it training data from the current policy induced by the parameters. Right? So the data doesn't have to be like as close as possible to the beliefs of the model about the world. That means that you can leverage data sets, right? I was telling you about molecules earlier. Maybe you already know about some high reward molecules or low reward molecules. And you can actually show these molecules to your model as a kind of grounding for it. That also means that you can use exploration. Kind of default strategy of taking random actions once in a while works really well. But of course, there's way more advanced exploration strategies that people have come up with. And we can take hints from reinforcement learning as well. Using replay buffers is a classic trick that can work extremely well to stabilize training, but using things like target network, intrinsic rewards. I'm going to tell you a bit later about this trick, QGFN, that we came up with, that also works really well in pruning the action space. But you can also learn from MCMC. In fact, you can apply both MCMC and a GFlowNet objective to kind of maximize your chance in certain settings where there's like local valleys of interesting objects. By kind of using your GFlowNet as a proposal distribution and then using some MCMC refinement step, you can get the best of both worlds. And of course, you don't have to train your policy from scratch. You can actually start from a prior and then fine tune as you would do an LLM, for example. So, yes. Sorry. All right. So just recapping once again, right? The general recipe here on the left is how do you define things. There was a question about like intermediate states. Generally, you would define the state yourself, right? It's part of the problem, something that we assume you have access to, right? So you would define the action space that yields the objects, think Lego blocks. You define a distribution over these objects, think a categorical distribution over these blocks, and then define some mapping from those states to a distribution over actions. So maybe just a neural network. Define a reward. This can be some physical thing, it can be another neural network that you've pre-trained. And you can use that that you use to train your GFlowNet rewards. And then the way you train, as I just mentioned, you sample, you might insert objects that you've sampled in your replay buffer, compute the reward, take a gradient step using the objectives, and repeat. So nothing hopefully too shocking. Yeah. So, okay. I have a bunch of slides about like in practice, what do you do during training, after training to assess the performance of a neural network? This is more or less a generic problem when you're training a generative model, especially training an energy-based model, because lots of problems arise in terms of understanding how well they're doing. So in particular, we're trying to fit an energy function. We're trying to fit a reward function. So the most kind of direct thing you can do to check if your model is working is just, well, compute P of X on some samples and see if it correlates with R, or see if there's divergence with the true distribution. This works, but only if you can actually compute P of X reasonably, which is not always the case. Right? So for example, in molecular settings, the subgraph of like ancestors of a state is reasonable to compute. So you can use basically dynamic programming to figure out all the ancestors and compute the probability of all trajectories in a DP way. But that quickly gets out of hand the larger your objects grow. Of course, you can like just stare at the loss as you would normally do. For losses that are not trajectory balanced, this can actually be a bit misleading. Local losses can be arbitrarily biased. But another thing that might be going on is that because this is an online, right, you're actively acquiring the data, your model is exploring the state space and getting rewards, your model might actually start discovering new things at some point, and then you might see that your loss increases. It's not your model diverging necessarily, it's just finding new things. Another thing that you might see if you actually train GFlowNets is that the magnitude of the losses seem like they can get extremely large, like 10 to the somewhat big number. This is not actually a problem, even though it may be a bit scary, because modern optimizers use second-order things, normalize by the magnitude of the gradients. So if you're using Atom, for example, training a GFlowNet is never a problem, even with these big losses. Another kind of thing you can look at when training GFlowNets is terminal flows, right? All the flows that go into a node should be proportional to the reward as well. So you can actually just look at that. Particularly if you have a state space with the stop action, right? The flow that goes along the stop action should be proportional to the reward. So it's a good way to test if your models are actually calibrated. Intermediate flows are a bit less obvious, right? They should be consistent. So if you have a transition S to S prime, typically you'd expect that the flow at S is greater than S prime just because S has more potential descendants, but that's not always true. Depends on the structure of your problem. And another interesting thing about these flows is that because they're related to the partition function, in a way they reflect how much stuff there is, right? So because they do this accounting of all the downstream flows, they're more or less counting modulo sum, dividing by the number of paths that lead to a place, the total reward available downstream. And again, the flow at the root as 0 is the partition function, which is literally how much total reward there is. And yeah, this kind of fun experiment you can do to test your code is to run it, but with a reward of 1 everywhere. And this should just literally count the number of accessible states if everything is correct. Speaking of log z, the partition function, Typically, you'd like start at 0 or close to 0, and you see that gradually the model kind of figures out that there's more and more stuff. As it explores the state space, it's able to count better how much each parts of the subspace have reward, and you'll see that you'll get these kind of behaviors. And in fact, if you kind of, here I'm plotting, I don't know if it's visible, but on the x-axis is the predicted log z by the model, on the y-axis the average reward that it's getting. And obviously not in all cases, but in some cases where the state space is very large and the reward is kind of fairly easy to predict, you have this very neat correlation where the more you train a model, or the better a model is, the higher its log z will be, because the higher its belief about the total accessible reward will be. Because you're training a policy, right? You have to monitor these things, right? So entropy, again, if you're familiar with reinforcement learning, can be a problem. It's much less of a problem, I would say, than in reinforcement learning to see these collapse, because typically you're not trying to train this optimal policy. You're not trying to find the thing that maximizes reward. Instead, you're trying to find this energy-based model that wants to go everywhere in your state space, or at least wants to go everywhere where there's reward. So if you monitor the entropy of the forward policy, it should go down with time, but it should also not totally collapse. And if it does, you might have too big of a learning rate or too much gradient clipping, these kind of things. And if you are playing with the temperature of your model, for example, that might kind of cause collapse. Yeah, so this is an open question, I would say, at least from my point of view, that is going to be really domain dependent, right? So let's say you're training an image generator, you might use FID scores or something more qualitative. But in general, there's not an obvious answer to what should a test set be. This is not just a problem with GFlowNets, a problem with generative models in general. You might want to assess whether your model is performing well on some kind of uniform sample from your state space. But if your state space is molecules, let's say, well, most of that is probably garbage, so fairly uninteresting. You might just kind of use samples from your forward policy as a test set. As long as you make sure you haven't trained on them, that's actually valid. But then you might entirely miss mode collapse, right? Or just lack of exploration. And then you might actually design a test set, right? So in the molecular domain, again, you might have a set of known binders that you hide from your model. And that can work well in assessing whether the generative model is matching the distribution well. But that means that you have to design the test set, which can be a lot of work and be quite non-trivial. As I mentioned earlier, you can actually measure P of X in certain cases. If the number of ancestors of a state is reasonable, it's something that's fairly easy to code and easy to compute. But in a lot of cases, that's not the case. So what you might do is do some kind of log importance sampling to try to at least get a lower bound on the actual probability of an object. But in general, these are pretty bad because they have bad numerical properties. So yeah, still an open question, I think, in GFlowNets and beyond, of like how to properly assess the performance of large-scale generative models. I'm gonna skip that slide. So, okay. I mentioned earlier that there's this thing called the backward policy. Again, a reminder, what this backward policy does is, given a state, it says, how should my flow backward to S0? And if a state has multiple parents, you might have a preference over which parents to choose, or you might just say, let's just use the uniform distribution. If you use the uniform distribution, in fact, it's kind of a very strong prior, because it says, I don't really care which path you take from S0 to your object. In fact, it says something even stronger than that. It says you should not have preference over path. You should want to take every path equally. And this has a really nice side effect that as you're sampling, if you take every path equally, you're kind of naturally exploring the space of intermediate states. And because your model is a bit random and a bit wrong, that actually encourages exploration implicitly. And that can be a very kind of strong thing to do. But from an optimization perspective, if you actually parameterize PB, well, you have the most degrees of freedom, and you can choose to regularize PBs in a certain way. Right? So, for example, this paper that says, let's be pessimistic. Let's kind of force PB to go along the paths that we've already seen because we know they're good. In some other instances, we have multiple things going on, right? These paths actually might correspond to something physical that you're trying to do. So you might want to actually train them to go through a certain route. The problem with that, of course, is that now you have more parameters, more degrees of freedom that can lead to more complex optimization. Yeah. And, oh yeah, in terms of fixed PB, right? The uniform prior or Gaussian prior, if you're in continuous domain, can be very strong. But you might also want to design it, right? So if you're in SD, for example, instead of using a Gaussian with a simple linear schedules, you might use exponential schedules or cosine schedules. And that might change what your prior pushes your model to have as intermediate states. All right. So yeah, just one quick note on continuous GFlowNets. They're fairly straightforward. All the math from the discrete case more or less transfers to the continuous case. You have to be a bit more mindful of these two things, right? That there's kind of a single Dirac S0 that matters to get right. And that if you define a backward policy, it must be compatible with a forward policy. Right? So all the states reachable by this backward policy should also be reachable via the forward policy and vice versa. Yeah, as I was saying earlier, you can actually run these things on very simple problems or images or sampling molecular conformers with no problem. Cool. So yeah, it's kind of a recap of some of the things mentioned, but yeah, I'm going to talk about these two papers. But before I do that, let's maybe just this recap slide. If you're lost or stop paying attention, this is what GFlowNets are, right? You have a problem, you have f of x, you want to sample from f of x. You might have not tons of data, but just f of x. You should try a GFlowNet. So I'm going to pause here before diving into some papers because I'm sure that there are questions.
Thank you. Question for clarification. You introduced the language of flows, and then operationally, it's conditional probabilities. You showed us detailed balance. You used Chapman-Kolmogorov, even though it was not explicit, but etc. All the mathematics we know from this type of stochastic systems. So I wonder, is there something in flows that goes beyond a conditional probability implementation and the mathematics associated with that? Or is it the same? Then it's also fine, but why do you use flows? And where does it go beyond?
Okay, I'm going to skip ahead, actually. Because that is a great question. So all frameworks tend to actually be other frameworks. That's kind of true in computer science in general, which is kind of a funny fact about science. So you're right that a lot of the maths I've used is like very straightforward in a way, and you can easily draw parallels with other frameworks. So kind of the broader answer to your question is this metaphor of flows that we use actually yield different objectives, different loss functions that we can apply to optimize our generative models. And there's some funny instances where, for example, with HVI, rational inference, one of the objectives that we use, trajectory balance, is equivalent, well, rather, the gradient of that objective is equivalent to reverse scale, but only in expectation. If you actually look at the learning process, it's different. The control variate is different. And I think that what the flow metaphor really enables is these different learning paradigms, different learning objectives, which really matter in terms of the learning dynamics. There's like really deep connections between learning dynamics and generalization in deep learning. And I think this is an instance where, I don't know in the long run what's going to be the best, but obviously this is a new way of looking at things. And I think it offers some dynamics which are better in certain scenarios. Does that answer your question? More or less. Okay. These are the questions. Microphone.
Okay, so when you're designing a molecule, for example, right, you have to consider things like, for every binding that you're having with another atom, right, you have to consider things like synthetic accessibility, how easy is to create a molecule, right? So you're getting at every stage, you're getting a molecule, right? So you have to consider, so how do you, in that path, right, when you're only considering the final reward and not what are the intermediate steps are, right? How are you incorporating that? And also the laws of chemistry, like, law of chemical equilibrium and so on.
Okay. There's multiple answers to that. So I'm not sure I fully got the spirit of your question, but I want to understand, you're curious about like, how do you even define the state space, the action space, right? Yeah, exactly. So actually, something I was going to talk about later is the kind of classical way to do this is either chain together a bunch of fragments or maybe chain together a bunch of atoms, create an atom graph, or even a smiles string, right? That's not great, right? You can do much better by having your intermediate state space be intermediate synthesis routes, right? So you could have your action space be actual chemical reactions that a chemist would do or a robot would do. And if you do that, use that as your action space, use some good reward as your reward space, as your reward function, you actually get much, much better outputs. But in a way, this is agnostic to the GFlowNet framework, right? But the framework does allow, it has the flexibility to apply it to all these things very easily. And these are convenient in particular because the transition space is very well understood. If you have a chemical reaction, you can understand what is the possible inputs, the possible outputs, the possible outcomes. You can choose from that in a kind of deterministic manner. And that is very compatible with the GFlowNet framework. Yeah, there's more questions in the back.
So thank you for your presentation. So my question was basically, how do you see this method for approximate posterior estimation of parameter, like for instance, the presentation of Marmaduke in the morning?
Yep.
So is a kind of a likelihood-free inference method? And what's the difference with the normalizing flows?
Mm-hmm.
And also, you need to define the energy functions. So basically, then how do you see difference with MCMC, like the Hamiltonian Monte Carlo there?
Okay. Let me again zoom through my slides. So there's this really cool, one of the first like GFlowNet derivative papers is called DAG GFlowNet and DAG GFlowNet, right? Like a Bayesian network. And it has basically shows that, yes, if you are able to estimate the likelihood of X given some parameters, then you can train a model, parameters and structure. Then you can train a model to optimize for the parameters in the structure, or sorry, rather, you can train a GFlowNet to sample parameters and structure in proportion to that likelihood. right? So you can generate hypotheses that explain your data. And much more recently, there's this paper that did this for astrophysics and black holes, right? So they just kind of defined a bunch of observables that they have in their data, which I cannot pretend to understand, right? But the extent of which I understand astrophysics is like PBS spacetime. But they did this. They had a bunch of data from a bunch of black holes, and they ran that GFlowNet, and that gave them a bunch of these MECs and DAGs, and then they went through the top 10, like, oh, this one makes a lot of sense. Let's kind of rederive our simulation or adjust our simulation, and they figured out that some were like really interesting ways of explaining different classes of black holes, right? So yeah, you can totally, if you define your problem well enough, use the GFlowNet framework to generate these structures and parameterized Bayesian networks. Yeah. There's another question right behind.
Thank you. Generic question once again. So at the beginning, you very much intrigued about saying that this approach can be applied to language,
Yes.
right? So I just wanted to ask, because everything is right now taken by LLMs, but what types of problems this approach can solve? Is it more like some supplementary component for biology, chemistry, or for example, they can be solve such a problems as, I don't know, states and dialogues in chat box, their modeling, and so maybe there are already some tests done with this approach.
Mm-hmm. Yeah. There's, again, multiple answers to that. Yeah, maybe first of all, like this framework is an optimization framework, right? So if you define the right reward, you'll get the right thing out of it. But yes, in practice, people are using GFlowNets right now to train LLMs to do things like proofs. And the way you would do this is, sorry, again, you sample maybe a chain of thought, a proof, and if you're able to verify it, then you can do some iterative refinement of the model, and eventually it's going to get better at math, right? There's another paper, which, do I have it here? Does automated red teaming, right? So you have some language model, sorry, there it is. You have some language model. It might not be great because it's a language model. And what you can do is train a smaller model to prompt it, right? Try to trick the main model that you're trying to evaluate, and use this kind of adversarial training setup where the reward of your attacker might be how toxic are the outputs or how wrong are the outputs. And the advantage here of GFlowNets, again, that being diverse and soft, is that they're going to probe the adversarial attack space in really interesting ways, in really diverse ways. And it kind of yields a nice distribution of potential attacks on an LLM. So yeah, that's like the first part of the answer is, yes, you can absolutely use these objectives in language models, very compatible with it. But the second part of your question is maybe even more meta, is like, can you go past maybe the language format, right? And just like I was saying for the astrophysics paper, because the GFlowNet framework is compatible with discrete and continuous things, in theory, and people are trying this, you might have latents that are more structured, more symbolic, right? There's a project to have some kind of model with Bayesian graph-like latents. It's kind of extremely hard to pull off, but that the math is correct, at least in this case. It's just the learning that's hard. We know we can converge the right things, and I think that's one of the interesting aspects of the framework here. So
Okay.
yeah, hopefully that answers your high-level question. Again, no question is too small. I have lots of things to say, but I think it's more interesting for you probably to guess.
I thank you for the talk. I have to say a lot of that went over my head, but I think what my question is about the design of the policy space, because I think that's the part where I don't understand anything because never did that kind of thing. So if we have a kind of model where we're typically working in a continuous parameter space and we want to approach it this way, how can I get my head around designing this policy space, which, if I understand correctly, is how you it's in that space that you construct the flow, right?
Yes, correct. Yeah.
And so are there, I know you made a lot of citations here, but I think I would be looking for some pedagogical material. Is there something available? Is it something that you can link to, or do you have a recommendation on getting up to speed on understanding the policy part of this?
Mm-hmm.
Thank you.
So the default thing to do is to do whatever diffusion people are doing, because if you're using a standard Brownian process, right, to model your drift, that works, right? We know that from image diffusion models and other diffusion models. But if you know more about your domain, you can do anything, right? So, for example, this paper on the right here, we are sampling conformers of 3D molecules, but in the torsional space rather than the 3D coordinate space. And then you don't want Gaussians, you want something like von Mises distribution because it is well defined over angles. But in a way, that is making those choices, I think, is part of the scientific contributions of these papers. Each distribution that you choose, the modeling choice that you make really matter in terms of learning dynamics and what distribution you're going to end up with. So you can be as creative as you want. In fact, I would argue you can be a bit more creative with GFlowNets than with standard diffusion, where you have to redivide a lot of math sometimes, which you don't have to do necessarily for GFlowNets. Yeah. But again, to maybe a kind of practical recommendation is, look at what people have done in the domain that interests you, and start there. If the answer is no one has ever done anything, start with a categorical for discrete data, Gaussian for continuous data. That's usually a good bet. Yeah. There's a question. Oh, I think you can activate your microphone.
Oh, I'm not really clear how this maximize diversity connect with the optimize the flow between the networks. Why is actually connect together, and do we have a hyperparameter actually control between the aspiration and the aspirations?
Okay, yeah, that's a good question. There's maybe let me just pull this. So the kind of side effect of modeling all the flows in all your intermediate space, and sampling as a function of that naturally yields the diversity that you're after, right? If you look at the rewards here, right, there's some maximum reward object, but you don't have all the probability of your policy going there, right? It's not just, oh, these two maybe are the best, so I'm going to put all the flow towards these two objects. No, I care about all the states and all their potential rewards, and modeling accurately the flow that goes to these states. And doing that will yield this kind of soft distribution where you don't just visit the argmax. And the other question is about like trade-off. one thing you can do is actually use a temperature parameter for the reward. You might actually condition your neural network here on an extra parameter that's the temperature. And if you do that, it's a bit harder because now the model has to learn to do something a bit fancier, but essentially it will learn to be more or less greedy as a function of the temperature.
I see.
If you put,
So basically, that means we have we can have a different float representing different possibilities. So we can, for each time, we choose a different row by the possibility. So we have maximum diversity, and
Yeah.
using something kind of like chaos divergence and for the temperature control for each of the possibility.
Yeah, in a way, like if as you're changing the temperature, you're changing the landscape, right? So your model might want to just go everywhere with equal probability. Or if you put the temperature really low, it's going to make your distribution, your posterior, very peaky. Right?
I see. Low temperatures means we focus on the best one.
Yeah, exactly.
And the high temperature, we're going to run the choose more different row.
Yeah.
Thank you.
Discussion over there. Thank you.
So you mentioned already that the Atom Optimizer can do a pretty good optimization, right? So I was wondering if having a higher order gradients or preconditioner can help us or not.
It's a tough question. If it's hard to beat Atom, I don't know if you've heard of Muon Optimizer. It does some weird matrix factorization. No one knows why it works. It works a bit better than Atom, if you're curious. But yeah, I don't have any practical tips here. I want to say that the choice of optimizer is going to relate more to the choice of function approximation that you're making. So if you're making a neural network, go for the usual neural network hyperparameters. Yeah, that's yeah.
Thank you.
All right. Cool. So I'm gonna keep going. Where was I? Yes, okay. All right. So, yeah, the rest of let's say for the rest of the hour-ish, I'm basically going to talk about a bunch of papers that I think are cool, that might interest you, that make connections with, oh, where is this going? That make connections with other fields or interesting otherwise. And for the second part of the tutorial, thinking of putting up some Jupyter notebooks and showing you how it's done. But that might depend on interest, of course. So please let me know if you have preferences either way. And again, please stop me if you have questions or if you want to throw the discussion somewhere. It'll be fun. Cool, yeah. So first paper, QGFN, was the idea. So far I've told you how like GFlowNets are diverse because they're energy-based models, and they can go and sample from everywhere, and that's great. The issue is that you don't always know in advance what your reward function is going to look like, and sometimes your reward function might actually make you waste a lot of time. So here's a kind of contrived example, but that's actually has, let's say, some connections with real problems. So let's say your agent is here and it has to choose to go left or right. And then if it goes left, there's these 100 doors and they all have reward 1. But if it went right, there's just this one door with reward 100. So if you think about the flow of this problem, the flow on the left has 100 units of flow. The flow on the right also has 100 units. So a GFlowNet agent would choose left and right with a probability 1/2, which means that 50% of the time it would get a reward of 1, 50% of the time it would get a reward of 100. it's not necessarily what you want, right? If you think about what a reinforcement learning agent would do, it would say, well, obviously I'm going to go right because action value of going right is 100, action value of going left is 1. I really don't want to go left. So what if we could kind of do a trade-off between these two things? And that's exactly what we do in this paper. Yeah, I'm getting to say things. But yeah, basically that's what we do in this paper. We're going to try to use both the Q function, which has its own problems, and the flow function, which has sometimes kind of over diversity problems, to try to get a best of both worlds. And not only that, but we're going to have a really simple way of controlling that greediness. So the kind of idea is that you train a GFlowNet as you would normally, but you also train the action value function. And in particular, instead of sampling on policy from PF, you sample off policy from this behavior policy mu, which we have several variants of. And the first variant is basically this P greedy. So if you're familiar with epsilon greedy, it's a related idea. But here we're going to sample from our kind of greedy Q-based policy with probability P and our GFlowNet otherwise. And this has kind of really good trade-off properties in terms of occasionally taking greedy actions and occasionally taking kind of diverse actions. But you can do a bit better than that in some scenarios. You can actually mask the actions. So in this p-quantile version, the behavior policy essentially follows the GFlowNet policy, except for actions where the Q function is predicting that the average reward is actually bad, right? So there's no descendants that you might be interested in. So don't even try going there, even though there might be a lot of flow there. P of max is the same, but kind of works with the ranking, with thresholding rather than ranking. And if you apply this to molecule generation, for example, you observe something that we initially thought was funny, that you both get more average reward, but you also get more diversity. And that's kind of funny in a way. That's unexpected, because you would expect that maybe what Q is doing is actually collapsing, right? It's better able to get these high reward because it's a greedy approach. But what it's actually doing is it's actually pruning the state space. It's saying it's pushing the model to avoid these low reward regions by making it prefer not taking these actions. And you can see that in this plot, right? So we're plotting the density of different reward distributions that we get as a function of the behavior that we choose. And you can see that if you look at the possible rewards you might get with the prune action in orange here, they're actually much lower than what you would get normally. So this QGFN policy, behavior policy, is effectively removing part of the state space that has lower reward than you might want. And of course, in the paper we talk about different variants, but you could come up with any kind of mixture that you want. They kind of have different trade-offs depending on the action space and the state space. And they all are kind of logical if you think a bit about it. But the most interesting part, I would say, is that now that you have these two things, the policy and the Q function, at inference, you can actually choose this trade-off. Right? So in all of these behavior policies, there's this little parameter P, which controls the trade-off between the two, between PF and Q. And changing that P will kind of make your policy go from being super diverse, having a decent average reward, to being very greedy and really collapsing in terms of the similarity between all the samples you're going to draw. Yeah, we thought this was really cool. Because essentially, again, like what Q is doing is predicting in a fairly accurate way what the average reward is. And so you can kind of dynamically prune away parts of your state space that have low average reward. And yeah, I was really kind of excited by this paper when we put it out because it felt really like a nice way to trade off between hard RL, which is traditionally seen as very problematic in terms of exploration and diversity, and GFlowNets, which are kind of the opposite and can be overly diverse in some some problems. And one thing that I think would be a cool extension of this work actually is that this thresholding function here doesn't have to be the action value function. It could be anything. In particular, you could potentially predict violated constraints of the objects downstream from an intermediate states and prune actions that might, in expectation at least, violate these constraints. And so, yeah, this might be applicable to things like more classical reinforcement learning at some point. Any questions? Oh, yeah.
So, if I understood correctly, this regulates this trade-off between exploration and exploitation. But aren't there similar knobs in classical reinforcement learning that do that, and how does that compare?
Yeah. How that compares is, well, we'd have to do the experiments, which we have some of it, but we haven't extensively run. But in principle, it's different at least. So in something like maximum entropy RL, you have a kind of flat, like flattening behavior if you tweak the entropy parameter, which corresponds actually to changing the temperature of the reward in GFlowNets. What this approach here does is actually different. So the posterior that is induced is quite different because it's based more on kind of making parts of the state space inaccessible entirely. Or, yeah, less likely in a more, let's say, discrete way, if that makes sense. Yeah, so it is, maybe to answer your question, it is different than the usual knobs that you have in RL. Either the entropy knobs or the kind of epsilon cover knobs that you'd have in epsilon greedy, for example. Those are different.
I'm wondering if we choose the most greedy policy, is going to slow the training times for that.
Yes. So usually you'd use different greediness at test time and training time, because at training time you might care more about exploring, covering the full state space than getting the best behavior. In fact, for some of the behavior policies that we came up with, it was way better to use the scheduling, where initially P was really low, so the model was just like a GFlowNet basically exploring everywhere. And as you train, you converge to this p-value. It's like 0.95 or something. That then makes the model focus on the high reward regions of the state space.
Thank you.
All right. So next paper I want to tell you about. This long title, but the kind of main takeaway from the paper is this method called relative trajectory balance. So what RTB gets you is posterior sampling, which is a fairly common thing that you want to do, but it gets you this posterior that is just a product of some prior that you might have and some reward function that you might want. And the way it does that is by taking this ratio of trajectory balance objectives and turning that into its own objective. And it turns out that this is a really straightforward thing to optimize. Regardless of how the trajectories are actually obtained. And so, yeah, sorry, zoom out. The kind of neat thing about this objective is that it's independent of the backward policy, which means that it's independent of how your flow allocation might occur, because that flow allocation becomes implicit in the prior that you choose to have, which is here p theta. So if you optimize for this quantity, essentially what your model is going to do is try to follow p theta, but also match this reward, right? So it's going to say only take the reward proportional fraction of your prior into your posterior. And again, you're going to have this partition function, or at least pseudo partition function here that you estimate. And if you minimize this quantity, you end up with the right posterior with the same mechanisms of GFlowNet and the same guarantees that you might expect. And if you call the Vargrad trick that I told you about earlier, it's also compatible with that. So you don't even actually need to model this partition function. It can be empirically determined with mini batches. And yeah, it allows people to do really cool things like optimize diffusion models to respect prompts better, or fine-tune language models to do things that we want. Like I was saying earlier, all these optimization of mathematical proofs and stuff like that is using this relative trajectory balance objective because it's a really principled way to actually get the right posteriors that you want. And it's really easily applicable to lots of settings. Basically, you just need a prior that you can evaluate probabilities on. But just for a trajectory, right, you don't need to be able to compute p of x, only p of tau. That's usually really easy. And of course, there's a bunch of priors out there. And of course, because you're doing this posterior sampling, or rather amortized sampling, you're unlikely to discover new modes, right? The posterior that you end up with is only able to kind of focus probabilities where the prior already gives mass. So that can be kind of something to consider before applying it. But yeah, it's since the paper came out, it's been applied on a bunch of problems, and yeah, it's been a fairly kind of efficient tool to take some prior and fine tune it in a more, as you would expect from the GFlowNet framework, a more diverse way, and a better optimization dynamics than you would get from, let's say, PPO. Yeah, just should notes on this paper. So as I mentioned earlier, GFlowNets are just a bunch of other frameworks. Really, all frameworks are kind of you can express them as variants of each other. So here I'll talk about 3 frameworks: rational inference, Maxent RL, and diffusion. So in rational inference, probably standard problem, lots of people in the room, but you want to express Q as some marginal over the potential latence, right? And in GFlowNet language, what this is just the trajectory that you use to generate your object, right? It's how you got through from your initial state to your object. And that Q here is really just PF. But that's not enough, right? What variational inference does is, given a data set, there's some kind of maximum likelihood. And here we're in a framework where we have rewards and all of that. So what's going on? So we're going to do a few additional steps. First of all, we're going to define P, right? So typically you want to minimize point of KL between the Q that you're learning and the true distribution P that might be exemplified by your data set. And as I mentioned earlier, it turns out that, at least in expectation, the trajectory balance loss, at least if the data distribution comes from this P, which corresponds to this PB in GFlowNet, has the same expected gradients than the forward KL. And the usual thing that we do is not that, actually, right? The usual thing that we do is sample on policy from the generative model and compute gradients from that. it turns out that this corresponds to the reverse scale, or rather, sorry, the gradient corresponds to the gradient of the reverse scale. And you'll recall that that actually corresponds to maximizing the elbow. And yeah, it's a really interesting link, I think, between two frameworks that, maximizing probability on the data set actually corresponds in a really neat way to fitting a GFlowNet. Yeah, I don't know. It seems super cool to me. And some other fun facts is that, well, why did I write it this way, right? Why is it the expectation of the gradient? It's because actually in this gradient, if you're familiar with things like likelihood ratio and reinforce, there's this control variate in these objectives, and the control variate that TB uses is kind of different than what you might use in VI or reinforcement learning. And in fact, if you think about the role of Z, the partition function in that expression, it acts as a kind of exponential moving average of the optimal baseline, approximation of the optimal baseline at least. And if you think about tricks like Vargrad, there's some kind of instantaneous approximation with kind of infinite learning rate of an ideal baseline. And you know, this is cool, at least to me, because it might explain some of the advantage that we see in terms of optimization dynamics and differences that we see also in terms of those dynamics. So one thing that exists in GFlowNets that doesn't quite exist in VI is this PB, right? But it turns out that there's also parallels that you can make, right? If you're training, if you're learning the latents at the same time that you're learning the main model, then it is like approximating PF and PB in alternate steps, which more or less corresponds to wake sleep methods. So this is also a very interesting connection if you're familiar with that. Another framework that GFlowNets are closely related to is maximum entropy RL. In fact, the GFlowNets kind of originated as a way to fix RL because we didn't want to do maxent RL for technical reasons, and we didn't want to do like hard RL because it would collapse and not be diverse at all. So here's why, right? So what maxent RL gives you, so things like PPO, is a policy where the probability of a trajectory ends up being proportional to the exponential of your return. The problem with that is we care about trajectories, but what we actually care about is these objects X. And if there are n trajectories that lead to the same object, you're actually going to have this really fun bias in maxent RL that the probability of sampling a particular object is going to be proportional to the exponential of the return, which is the reward, right? But multiplied by n. So, you know, in this smiley face case, this is not too bad, maybe because your state space is small. But if you're doing something like combinatorial optimization, generating molecules, this n can become extremely large, extremely fast. And this is a pretty bad bias that we can measure and that we've measured in the early papers that maxent RL has. That kind of are different from reinforcement learning. Another difference is that if you think about MDP modeling and what it means, here in GFlowNets, we're basically assuming that the MDP is known and deterministic, or at least locally known and deterministic. And knowing this fact is actually extremely helpful. There's some literature in reinforcement learning that suggests the same thing, that if you do know that your MDP is a certain structure, or even better is deterministic, there's some extra optimization tricks that you can do that kind of give you better convergence guarantees. And so with the flow accounting and the backward policy that GFlowNets are using, that basically allows them to correctly give this unbiased sampler, right? And by unbiased, I mean just not biased by the number of paths that lead to a particular object X. Just going to pause here in case there's questions. So, of course, there's a fix. You can actually do maxent_RL with a little correction. And that correction is actually extremely close again to the correction that you would see in a GFlowNet, right? In a GFlowNet, if you recall detailed balance, you have this log ratio of PF and PB. You can actually slip that into an intermediate reward in the max and RL language and end up with the correct sampling, right? So what this extra term does is implicitly in the reward account for the number of paths that lead to a potential state. The caveat here that differentiates maxent_RL and GFlowNets is that PB needs to be fixed, right? So unlike in GFlowNets, we can optimize at the same time the forward and backward policy. Here you can't. Important difference. GFlowNets are just diffusion models, right? I think I was saying earlier that you can kind of apply the same math of starting from your initial state as a Gaussian, final state is some point on your data distribution, maybe an image or a molecule conformer. It turns out that the noise schedule that you might be used to in diffusion models is really just a specific choice of the backward policy, right? The noising is same as deconstructing in a way. It also turns out that if you take a continuous time view on continuous GFlowNets, with the right choice of PB and PF, the drift that you learn ends up just being the score function, which is what you'd expect from a diffusion model as well. So that's kind of good news in terms of the models, the modeling frameworks matching. And yeah, like I think as I was also saying this earlier, using a Gaussian is a kind of a special case, right? And in theory, GFlowNets are way more general. You should be able to fit, to use any parameterization of your forward and backward policy that you want. Although in practice, Gaussians work extremely well. So it's kind of an interesting double-edged sword that the framework allows for more flexibility, but that flexibility might be harder to optimize for. So yeah, GFlowNets are just equivalent to some other frameworks, but at the same time, not really. As I was mentioning, the fact that we can have this free backward policy is really a unique feature. We don't need wake-sleep type loops, right? We can just optimize everything jointly and it still works. Another difference between some of these other frameworks is that the objectives can be somewhat arbitrarily off policy, although obviously there's kind of dynamics caveats to that. The parameterization can be somewhat arbitrary, maybe unlike normalizing flows where you need a special parameterization where you have to be able to compute the Jacobian. And flows, again, correspond to some interesting quantities, but the translation is not always trivial. And if you compare it to the MLE kind of setups, it is different in the sense that you're able to do active data acquisition. So yeah, a few more papers talk about. There's some interesting caveats if you're working with symmetric objects that you have to account for to actually get the correct counting. For example, in these graphs, you might have actions that lead to the same next state that look like they're different actions. As for example, here on this triangle, whether you add an edge to 1, 2, or 3, they all lead to the same next state. This is something that in theory you have to account for. By the way, this is also something that shows up sometimes in graphical models. That's something you care about. A little while ago, we also did a paper on kind of trying to understand what are the generalization dynamics and behaviors and how we can try to understand them. Turns out that, at least from a kind of deep learning perspective, if your model is able to fit the reward, if your architecture is able to fit the reward, it will probably also be able to fit the GFlowNet. And the second result we got from that paper is that basically on policy is a very good and safe choice. Except for a few exceptions, if you have a lot of insights into your problem, you can actually do a bit better than on policy. But in general, kind of naively deviating from on policy can be almost arbitrarily bad. Another kind of cool connection, again, between flows and value functions in reinforcement learning is that the flow function corresponds to a scaled value function, but specifically, it corresponds to the scaled value function of the uniform policy, which, if you're familiar with reinforcement learning, might sound a bit weird, but I think is actually really insightful. And this is true in both MDPs that are trees and MDPs that are DAGs. And final little cool papers is that I kind of introduced the GFlowNet framework as you have a DAG and there's pipes and flows and all of that, and you wouldn't imagine cycles in there. It's kind of incompatible with our notion of how pipes work. It's also incompatible with the way the math of GFlowNet works. But recently, people derived extensions of GFlowNet for networks with cycles, and turns out that it's actually fine if you do the correct modifications, things still work out. And there's two, maybe three really interesting insights from that the policies that you get are still convergent with a really kind of easy criterion, is just that you need to have finite flow, right? So you could imagine some extra flow kind of magically appearing because it loops back into your flow network. But as long as that's finite, you're guaranteed to have a sampler that does the right things. And the kind of DAG solution with no cycles actually turns out to just be a special case that has just the minimum total possible flow. And it turns out that also this minimum possible flow corresponds to also the policy that has the minimum trajectory length in this cyclic MDP. Cool. So yeah, check. Sorry, just checking what it would make sense to present at this point. I'm wondering if we should like take a break now and come back for GFlowNets in the real world and other speculations, because it's already been an hour and a half, and I'm sure that some of you are losing focus. Yeah, I see nodding. Cool. All right, so let's do that. Let's come back in, I guess, an hour-ish. This is the length of the break. There's an organizer nearby. Will be a bit more practical and speculative. And once again, if these slides inspire you to ask a question, please do. Yeah, lots of interesting parallels and things going on in these papers. So the first paper I'm going to talk about is this GFlowNet model. And it is basically a model to do molecular design. But as I think I was mentioning earlier, instead of using a kind of abstract, unrealistic action space, here we use these synthesis pathways. So, why would we do that? Basically, the molecules that humans could design have been designed, and now we have to kind of search the huge space of chemicals to figure out new drugs and new things that are interesting. And we have to turn to generative models because there's only so many humans and we've run out of imagination. But the problem with a lot of these generative models, like big transformer that generates molecules token by tokens, is that they tend to generate molecules that just could not exist. Like if you try to make them, they'd explode or just degrade in a few seconds. And we call that a synthetic accessibility problems. Basically, sometimes we don't even know how to actually make them. So the kind of thing that we set out to do with this paper is, what if the action space itself was chemical reactions, right? Things that we know how to do in the lab. Then kind of necessarily the things that the model ends up generating are doable. The problem is that this action space is kind of weird and very constrained. So maybe it's going to be something that's hard to realize for machine learning. And yeah, again, like the kind of classical way to design molecules is extremely weird from a synthesis point of view, because you're just plugging in Lego blocks together if you're doing fragment-based design, or just plugging in molecules atoms one by one if you're doing atom-based design. And these have kind of no bearing on how you'd actually construct a molecule. So instead, what we're going to do is that you learn to generate from databases of reactants and reaction patterns. And again, with the GFlowNet idea, right, match a reward and get the diversity and the exploration that you get from GFlowNets, only with this constrained action space. And if you do that, of course, you don't have access to the full chemicals space anyways, but at least if you do this correctly, you can actually start creating things that you can buy pretty quick. And either way, this like most constrained space is still extremely large. Depending on the blocks that you use, you might have trillions or hundreds of trillions of possible molecules. So not something that you can enumerate and screen very easily. So what is this action space here? If you're familiar with chemistry, right, you have these templates, which you can think of maybe as regular expressions, but for graphs and for molecules. And so what the model will end up doing is look at the current molecule that you have, right, and decide, okay, do I want to stop? Do I want to add a reactant? Or maybe do I want to do these bimolecular reactions? There's a question, yes.
Yeah. So molecules are usually in pharmaceutical industry developed based on what are called active pharmaceutical ingredients, APIs, right? So in that case, like, wouldn't a fragment-based design be more useful than going for a reaction-based?
I mean, they're almost the same, I want to say.
But I
It's just,
saw in the previous slide, if you go, I mean, you had this spectra, right? Yeah.
yeah.
The spectra, right? So you have atom-based, fragment-based, reaction-based, right?
Oh, do you mean that you could do syntons here?
Yeah. So I would say that, because, when you're actually designing a molecule or manufacturing a molecule in a pharmaceutical industry, you're using active pharmaceutical ingredients, APIs, which are basically fragments.
Yeah. So syntons work pretty well, but they have their own problems. In particular, if you look at like the syntons from enamine, there's like a lot of them, because they are also a combinatorial expansion. So actually, the kind of reaction approach to this is more of a middle ground that's more tractable for neural networks. But in a way, they're equivalent problem where you just pre-compute the branching, right, that yields these active pharmaceutical things or syntons. But that would also be a valid way of looking at it. Yeah, maybe one thing that you wouldn't get with syntons is this, that if you're interested in a more generic case where you don't necessarily know what the manufacturer you're working with has or might have or might be able to do, you can actually get this retrosynthesis policy for free. So, okay, this is actually maybe something that is important to mention here. I'll try to explain at a high level if you're not familiar with chemistry. So there's two problems in chemistry kind of in this space. The first problem is just finding what are the good molecules. The second problem is, if you give me a molecule, how do I actually build it, right? And that's called retrosynthesis. It's like going from molecule to the planning of the molecule. And here, if you recall, in GFlowNets, there's this backward policy, right, that tells you how to go backwards back to S0, that does this flow allocation. It turns out that here the backward policy has a really specific interpretation in that it is the reverse of these chemical reactions, right? And this is essentially, with some caveats, of course, but it is essentially what retrosynthesis is trying to do. It is saying, how do you go back to the origin? How do you go back to your basic building blocks from a molecule? And so it is really interesting that when setting up the problem in this way of doing both forward and backward modeling, we're kind of solving these two problems at once in a single model. And on top of just having this regular backward policy and fitting it with the GFlowNet objective, we can fit it to do other things. Because remember, the backward policy in a GFlowNet can be whatever you want, up to certain things, but it's like a free variable. So you can choose to influence it in the ways that you want. And something that we do in particular in this paper is that we train this backward policy, which will give you different ways of building the same thing, right? We ask it to optimize for this route reward. So we want to maximize yield and minimize cost. Right? This is again an optimization problem. We can optimize this with RL or with GFlowNet again. And this ends up like biasing the backward policy towards things that are more accessible, cheaper to synthesize. Yeah, it's kind of a interesting example, I think, of how both the forward and the backward policy being potentially free parameters in GFlowNet can have some interesting consequences. So the first results we had with SynFlowNet were like on these story problems, and we showed basically that if you compare that to fragment-based approaches or other approaches like reinvent, that you would get very sensible molecules that are kind of trivially easy to synthesize because they have a corresponding route that makes sense. Even if the software that we use, for example, here we validated our molecule with this kind of standard software in the field called AISynFinder, and it would find different routes than what the model itself has learned to propose because it used different templates, for example. But if you compare the routes that are found with for the molecules that the model proposes, they're much nicer and much simpler than for a generic fragment-based molecule. And so, again, like, I think this SynFlowNet paper is a really interesting and kind of emblematic application of the GFlowNet framework. There's a complex combinatorial problem. Diversity is extremely important, right? Because again, we're in molecular design. We're not sure exactly what's going to work because our reward functions are approximate. The action space is very weird, very constrained, but that's not a problem because it's compatible with the framework. And again, this is a place where learning this backward policy is meaningful, which technically, for various reasons, is extremely hard to pull off with something like reinforcement learning.
So one of the things that happens when you design a molecule is that the end product, right, becomes toxic, right? Or it has.
Yeah.
So is there anything that you can do in the path, right, from when you're either to prevent molecules getting generated that are toxic?
Do you mean at the end or the intermediates?
The end result is toxic. Intermediate may also be toxic, but end result becomes toxic. Ultimately, you want the end result not to be toxic, right?
I mean, I want to say that's someone else's problem, but no, it's the problem of whoever's designing the reward. Right? So we have generic toxicity models at Recursion, but it's kind of just folded into this R value that we give the model. Or if we do multi-objective design, then you end up generating the Pareto front of like toxicity versus binding affinity, for example. But it's, I wouldn't say orthogonal to the GFlowNet aspect of this work. I don't know if that makes sense. But yeah, it is obviously something that we care deeply about. This question back.
Yeah, so I'm not very familiar with molecular design and these chemistry models. So following up on this question, can you comment a bit on how we formulate the rewards for this type of model? So what's what we try to optimize for here or penalize?
Yeah, that's my next slide.
Perfect.
There's many quantities that you might optimize for. And in this very recent paper from a collaboration between MIT and Recursion, the group trained this very large kind of AlphaFold-like model, but specifically on protein and molecule complexes, right? So you have a small molecule, that the thing we're trying to generate, and you want to see how does it affect a protein's shape, right? Does it prevent the protein to do what it would normally do? Because sometimes, let's say you have a cancer, what you want to do is like target a specific protein that helps the cancer cells reproduce. If you can turn that off, then you have cancer drug. And this Bolz-2 model basically is predicting the binding affinity between these small molecules and this big protein. And this binding affinity, you can literally use it as a reward, right? So you want the affinity to be as large as possible so that when the molecule finds this drug, finds this protein, it sticks to it and it disables the protein. And typically the second aspect of this, which is related to toxicity, is that you typically have one protein in mind. So you want to maybe disable just the protein that is responsible for the cell division, but you want to leave everything else untouched because, well, maybe you don't want to kill the human that is ingesting the drug, right? So that's usually the challenge. It's like this selectivity of the drug compound to target this one thing while not touching the other things. So that's in drug discovery, that's more or less the usual setup.
So I come from more of a robotics background, and they're making up the rewards. It's kind of like alchemy. So you need to like play around with a lot of components to come up with something that sort of the model doesn't hack or doesn't cheat with. So is this analogous here in molecule design? Do you need to like come up with weird regularization components in the reward so that the model, that the molecule doesn't become whatever toxic or
or I want to say yes and no. Yes, because we don't understand biology that well, right? So not only do we not understand it, but like, even this I don't know, billion parameter model of the protein is not that accurate. So yes, there's a lot of like adding other quantities, doing a big multi-objective optimization where you have lots of different things that you care about just to help the model figure out, okay, what's the right region of solutions. But no, unlike robotics, there's like a ground truth, right? So the thing that they're comparing against in this paper is ABFE, which you don't need to understand what it is, but it is something that's computed by literally running a physical simulation. And that's kind of a ground truth. You know exactly what you want to happen. It's just running the physics forward in time, and it costs a lot of compute, but it's doable. And in that sense, like the kind of ground truth quantities are connected to physics, I want to say. Whereas in robotics, you're trying to make a robot. What does it mean to walk naturally? It's not clear. What does it mean? I remember in my lab, there was like automated wheelchair navigation and in social settings, right? What does it mean to not break a bubble of people conversing, right? Like these are more fuzzy concepts that there's not as easy a reward to design for. Hope that answers the question. Okay. Yep.
So maybe I have a question regarding the FlowNet itself, like dynamics. So I was wondering, since you formulate already the reward function that seems to be differentiable, why not to use a gradient flow normally to train it?
Okay, so the first answer is this is a discrete problem. So the gradient information doesn't actually tell you that much. Now that's actually a lie because there are gradient-based discrete optimization methods. I'm not a big fan of them in practice. In these kind of settings, they don't work that well. That's
Okay,
debatable,
but
of
like
course.
the discrete like can be relaxed and then can be trained as well.
Yeah.
It's like one of the well-known tricks.
Yeah.
So it's doable still, like
It's doable, but I am not aware of it working in the real world.
Okay, thank you.
Yeah, just maybe to add another comment on it because it's not in my slides. If you're in a continuous domain, there you can use the gradient information, and it's really helpful in certain settings. Like if you're doing diffusion, you might want to do like Langevin sampling. We might do things like target score matching, but there's a GFlowNet version of that. Yeah, then if you have the gradient of the energy, it's really useful.
Is it possible to use something like a reparametrization trick to answer his question, right?
So yes, but it doesn't work as well. Like something that was actually popular in like, I don't know, 2018 was this latent space Bayesian optimization. So like people would train a graph autoencoder, right? And then you have this continuous space for your graphs. And in that space, you can predict a reward. And you would think, okay, it's a continuous space, so I can just navigate to SGD basically to optimize for the properties that I care about. And it turns out that that doesn't really work because the latent space captures too much of the structure and not enough of the activity, right? So your kind of structure-activity relationship is extremely discontinuous, and it makes Bayesian optimization in that latent space not work really well. There was a question earlier somewhere. I don't know if people got shy. It's okay. Cool. All right. So yeah, kind of takeaway that I don't know if this is the right crowd because maybe this is already obvious for you, but often in machine learning, I think people underestimate the importance of MDP design. There's some instances in reinforcement learning, but this is true in GFlowNet as well, where like just doing some very minor changes to the action space dramatically speeds up learning. And if you do this right, if you constrain your action space in the right ways, you might actually end up with some good guarantees or like the ability to encode the right priors. So just a little parenthesis here to say that designing these action spaces, I think, is a scientific contribution, like paper-worthy contribution if it's done well in itself. So, okay, GFlowNets been used in a bunch of things, so I'm gonna talk about them. I think I've already shown some of those slides, but maybe worth recapping. So we've been able to do protein design in basically two ways. You can learn from scratch, right? You have your transformer initialized randomly, it works fine. We can do active learning. We do pretty well in terms of diversity again and novelty and reward. So that's great. But something that also works well, of course, is working on a pre-trained model and fine-tuning it. So you might have your ESM fold trunk pre-trained, right? That's a protein language model. You can just sample that or use that as your initial parameters, and that works pretty well. The other way to design extremely long sequence is editing, right? So you might design a policy, which you can think of as a diffusion model again, where you start with something, but instead of being noise, it's an actual image that you're doing, let's say, in painting in. Instead of being an image, of course, it's a sequence. And this is a kind of interesting strategy. It's closer to MCMC maybe, but it still gives you this good trade-off between staying close to sequences you know work and discovering new and diverse sequences. Another very interesting application has been the application to LLMs. One that I've highlighted here is automated red teaming that I was mentioning earlier. But again, just to recall, right, GFlowNets are pretty good in terms of like diversity and being soft, right? So not just looking for the highest reward example, right? So here you might want to find all the attack surfaces, but you don't necessarily want to always find the the attacks that make your model go absolutely crazy. You might also care about the instances where it's saying a bit about bad things, right? You also want to find this, and the GFlowNet approach will yield that more easily than something like PPO or HardRL. It's also been used in causal discovery and astrophysics in a few cases, because we have some collaborators from the University of Montreal in the astrophysics department, and they've been really interested in that. As I was saying earlier, right, some big supermassive black hole data set, and using these tools allowed the team to generate these competing hypotheses that the researchers, the astrophysicists can then take and understand and evaluate with their own lens. And that allowed them to basically realize, oh, hey, there's these two clusters of black holes that formed with entirely different mechanics that are now compatible with their in silico simulations. You can also use GFlowNets to solve inverse problems with something like RTB. You can try to recover kind of the latent variables of your data distribution. So here, for example, you have a lensing problem. So there's a galaxy behind another one, and the galaxy kind of bends the light. And all you see is the bended light, and you want to figure out, okay, what was the original galaxy? And what's the lensing field? And that's something that you can solve relatively easily with the GFlowNet setup. Another related to drug design, problem related to drug design is material design. There's a team at Mila that basically is kind of focused on climate change, and it's trying really hard to push the field in terms of design for things like batteries and carbon capture materials. And they've been able to basically set up the problem and train a GFlowNet to sample crystal structures that are reasonable and that will form well. And basically the next step is to kind of extend that to all sorts of properties that you might care about in crystals. So, okay. If you're curious about, what's next for GFlowNets, there's a bunch of kind of frontiers that are obvious to me, but of course there's way more than there is here. The first one is maybe that there's this like one objective that seems to work extremely well. And it is very satisfying to see, GFlowNets applied in the real world and work well. But it is unfortunate, in my opinion, that this kind of approach throws away some of the really unique and interesting elements of the GFlowNet framework. So I think our community needs to understand a bit better why this happens, why we can't do better, why we can't actually leverage the flow predictions to do, generate really long sequences or something like that. Yeah, this is something that I'm hopeful people will keep working on. It seems pretty clear by now that GFlowNet versus like RL and traditional combinatorial optimization methods, it really has an edge in certain scenarios, especially where there's a lot of structure to the problem that something like a neural network can capture. And people are pushing combinatorial optimization, with GFlowNets on all sorts of domains, which is really cool. But in contrast to combinatorial optimization, continuous GFlowNets have been struggling a bit more. They've been extremely successful for fine-tuning. So we fine-tune image models, for example, and that works very well. But training a continuous GFlowNet from scratch, especially in larger scale applications like 3D conformist sampling, has been a bit more challenging, and it's still not clear why. And then there are domains where the flow function itself is meaningful. Right? So in particular, the flow function represents some kind of free energy or some marginal probability in certain problems. That can be really useful, but it hasn't been used a lot. There's basically this one paper that has used the marginal probability very explicitly. And then, of course, we're not done developing new objectives. There's some very recent papers that were at ICML this summer that do really funny stuff like gradient-based optimization or kind of replacing the usual log ratio with F divergences that can have some really interesting side effects. So yeah, like there's still still some really cool work to be done, I think, in that space. And yeah, oh yeah, one more slide on like this marginal probability stuff. So imagine that X is just like a bunch of these variables that you're maybe sampling in your Bayesian network. If you have a partial sample and uh, some of your variable are uninstantiated, partially instantiated, right? Then the flow at a state, because your energy is a log probability, your flow of a certain state is the sum over all the descendants, right? If you recall, and that's a marginal probability, which is really cool. And it led in particular to this cool paper that did some really cool inference in sparse graphical models where you might have like 10,000 variables, but you only want to instantiate a few because they're for some data point, the ones that matter. Can be a really efficient trick. So yeah. Before I move on to more broad speculation, I don't know if there's questions on these topics.
I just wondering if that possible to do a dynamic graph for GFlowNet.
Yes, what do you mean by dynamic graph?
Like if we like kind of like doing the training, we split the node to half or the more, or we just doing some change the edges between the nodes.
Well, so you never like this graph of states is never in memory, right? It's only ever implicit because you have some neural network that models it. But what can be dynamic is the state space itself, right? You could have a conditional model. So actually, in this particular instance, in SinfulNet, the model is being told, here's the list of reactions, and here's the list of building blocks that you can use during inference. So during inference, you can kind of dynamically change the graph to suit whatever needs you have at the moment. But in terms of splitting the graph, there's actually another interesting thing you can do. There's this, I think it's called like embarrassingly parallel GFlowNet paper, and they come to the realization that if there's some branches in your state space that are independent, you can actually train these n-independent models in parallel and then kind of join them into a joint distribution. And that's obviously very efficient because now you've separated your concerns into n different models. Of course, you might lose in terms of parameters because you no longer have shared parameters between the different state spaces, subspaces rather. But it's still something that's possible to do and in some cases very efficient.
See, thank you.
Yeah.
Thank you for presentation. I have a question about the last slide. You
here or
the last slide you talk about like this one, yes, and what it means that you have like a partial state and you're optimizing over a partial state. What do you mean?
Right. Okay. Do you remember the smiley faces example?
Yeah.
Right. So let's say you've just chosen if the mouth should be happy or sad. Then that's like a partial state. That makes sense? So the flow of that partial state is a kind of marginal flow, marginal probability in some senses of the downstream things of instantiating, right? Of choosing the left eyebrow and right eyebrow.
It's like freezing a part of the flow. You are freezing a part of the flow and working on it with a part of the flow?
Not exactly. It's what these flows in intermediate states represent, right? What I'm trying to say here is, in certain problems where your energy function is log probability, if you've only made certain choices, then the flow is equivalent to a marginal distribution, marginal probability. Right? Let's say you have two variables, right? And you want to model P of x1 and x2. Then one way to model that is P of x1 times P of x2 given x1. So what I'm saying is this P of x1 is the marginal over all x2. That's what this flow represents.
Okay. I will ask after some.
Yeah, please come see me. Cool. All right. Okay, so yeah, why? Yeah, these slides are basically like why I'm excited about GFlowNets and the future of GFlowNets. A lot of the papers I've talked about and that you might see using GFlowNets are these like object discovery papers. So you have some molecule you're trying to find, some protein you're trying to find. Like basically all I've told you about is kind of directly applicable to this setting. And then there's like a higher order setting, causal discovery, very cool, very impactful, but we're kind of still at a small scale where if you go beyond a certain number of variables, things start being kind of slower and even breaking sometimes. But some things might work better. In fact, I think right after this, or maybe tomorrow, I forget, we might have a lecture from Bernard Shalkov talking about causal representation learning. So, you should attend that if you're interested in that. It's a really cool kind of alternative way of thinking about the problem. But I think the next thing that we need to learn how to automate properly with machine learning and maybe with GFlowNet kind of objectives is this hypothesis discovery. And it's kind of a fuzzy thing. I'm hesitant to try to describe it too closely, but it's kind of what's the next layer above causal discovery is like, how do you learn to represent stuff? And represent stuff in a way that is kind of Bayesian about how the world works. So, in GFlowNets for science, you have usually some level where you have a true reward, right? So physics is like the canonical example here. If you have a force field, then you can train a Boltzmann generator on this because you have the energy and it works out, you get the right things. You can go even lower level to DFT, right? Learn to generate crystals and materials. And it's kind of really cool because the ensemble properties of these distributions can be modeled as flows. But that's not quite what hypotheses are. And I think, in fact, designing the right space of hypotheses is going to be more or less like MDP designed, right? I know that I'm maybe re-explaining what Bayesian networks are and all of that, but I think this is doable at a higher level, right? A hypothesis is just something that explains the data, something that says, okay, I have some observations and the likelihood of those observations might be high. And these things might be local, right? Like a pathway in biology, or global, like your hypothesis might be a full graph, deep neural network. And I think what's important, and maybe even a lesson that is not always obvious in these like Bayesian network sampling, is that we don't just care about finding one hypothesis. We really care about distribution of hypotheses, because there'll always be, well, if you're Bayesian like me, there'll always be some uncertainty about the world. And so if you're kind of being scientifically honest, you should be able to compute things over the space of probable hypotheses. And this ability to marginalize some quantities over hypotheses is something that GFlowNets give us, which I think, again, has been underexplored, but is potentially extremely powerful. If you'll allow me to kind of sell why I think recursion is cool and why I work there, right? Like, we have tons of data about different modalities. We have phenomics, genomics, transcriptomics, and we want to use all of these different modalities to kind of generate hypotheses about cell biology, generate hypotheses about chemical interventions we can make to the cells, drugs, right, that would cure certain diseases. And those rely on making the right biological hypotheses. And it's really fun. Like, we almost certainly have to be Bayesian because all this data is great, but it's super noisy. There's never going to be enough information to get like one global minima, one true model of the cell. So what we should probably aim for, right, is being Bayesian, is making multiple diverse different bets about what the true model of the world is. And we recently put out this paper that kind of formalizes this idea of a virtual cell in that context of like, how do you take all the different layers of data we have and learn to generate these hypotheses at scale with machine learning in an automatic way that doesn't depend necessarily on humans specifying, this is the right level of abstraction or not. And I was thinking earlier, you got a tutorial about virtual brain. It's not so different, right? You have this kind of data model predict loop where you go in and refine your model. But in this case, we're hoping that machine learning can do that loop automatically, because we basically have all the ingredients, more or less, to achieve that. So once again, like I'm pulling my earlier slide of why we came up with GFlowNets, but this is actually true about this hypothesis, this discovery business, right? The hypotheses that we make, they're bets on how the world might work. But unlike quantum physics, we will never be able to verify these bets at 5 sigma. And so we must cast a wide net once again, right? We have to be able to compute if our hypotheses are likely, but also compute outcomes for different potential likely hypotheses. So once again, we have to be able to do this marginalization business that flows, in principle, should be able to do. Yeah, one last hot take. I think like LLMs are early evidence of that. People have started doing like reasoning and fine-tuning reasoning and chain of thought and all of that. And I think, in my opinion, reasoning is some kind of primitive version of this generating hypotheses in a kind of naive way, right? You can think of each chain of thought as enabling the likelihood of the data, of the answer to the query that the LLM is making. It's kind of a self-discovered hypothesis, in my somewhat speculative opinion. The problem with these LLMs is that they don't really actually explain the data. They're just correlations of the data, right? The way they're trained is basically, oh, this prompt, this chain of thought makes the answer more likely, so you should generate it. It's just correlative. It's not actually causal, at least not yet. Even more speculative is this whole system 2 business that I haven't been, super into, but that I know some people at Mila are working on, right? There's a hope that because GFlowNets are able to do this discrete combinatorial optimization very well, that we might be able to automate latent graphs, latent graphical representations of the data, of the observations, where the energy, again, is something like, does this latent explain the world? This really seems like just amortized inference, but in latent space. So yeah, I think I'll stop here at least. And yeah, so first, thanks to all my collaborators. This is, of course, like a super big group effort. A lot of these folks are at Mila, but also elsewhere now in the world. And yeah, so thank you. Just want to say, I do have some like Jupyter notebooks, but I know that they're rarely useful in practice unless people are already super into a subject. So I might kind of pause there, take questions. We have 45 minutes-ish before 5, but we could stop here unless people are really excited to do some Jupyter notebooks. So yeah, thank you. So any speculative questions? Or understanding question? Maybe I just said a bunch of things and they didn't make sense.
Yeah, so thanks for the very nice tutorial. So in the previous session, you mentioned a paper that used the GFlowNets with a continuous state space for image generation or at least preference alignment of images. I think I didn't get it correctly. So could you go over it like in a bit more detail? Because I'm actually pretty curious to see how you formulate the transitions and the status space in this continuous setting. How is that parameterized and so on?
Yeah. So in this particular paper, well, okay, there's, let's say, two things that we've successfully applied GFlowNets to. The first is like this fine-tuning paper. So you start with a prior, and you want to find a posterior that matches some reward. So here your prior might be a pre-trained diffusion model. So what is the action space? Right, it's the reverse diffusion. It's doing these little Gaussian steps that eventually lead to the data distribution that looks, something nice. Your reward in this case is forgetting the name of the model exactly, but basically you might prompt, in diffusion you have like a text that that you condition your diffusion model on, and you might have another model that judges whether the image corresponds to the text, and that's basically your reward signal. So, for example, for the green rabbit column, the first row is the prior, right? So green rabbit, it kind of doesn't get it, except in a few cases, it just has grass. And this is like the baseline fine tune, this is the GFlowNet fine tune. And the reason the model is able to do that is that the kind of reward model is able to successfully say, is the rabbit green or not? But more generally, you might use different rewards if you're able to measure qualitatively the whether the image makes sense or not, or if you have some other kind of model labeling, you might look at the overlap or the agreement between the prompt and the labeling of the image. That can also be a good reward signal for that model.
All right. Yeah. Thank you.
Okay.
Yeah, first of all, thank you very much for this great presentation. About your point with the hypothesis discovery, that's actually very interesting. So, do I understand you correct in that you are trying to create a maximum likelihood estimator via GFlowNets to essentially find a hypothesis, whatever that means? Because I'm also not quite sure on how you actually, what you mean by a hypothesis. Like, what is the estimate then of that maximum likelihood estimator then in that case? Like, what's the data structure, for instance?
Yeah. To be honest, I also don't know, right? The speculative part of the talk where I'm allowed to say nonsense. But no, like, I think what I'm trying to say, and this is maybe related to, I'm gonna get to it. This is related to causal representation learning, in the sense that the traditional way of like defining the variables that you care about and then doing some maximum likelihood estimate with those variables is very limited because the world is way more complex than those particular variables, right? In virtual cells, if you kind of stop at the 1 node equals 1 gene level, it's going to work, but not very well, right? And my argument here is twofold. First, we should automate finding what these nodes are. Like these are latents, and we should let them be latents, and not try to impose the abstractions that we humans came up with to explain the data. And second of all, we need something that I don't think we have done very well, which is partial instantiation. The best that I'm aware of that we have is this Delta AI paper. If I can find it. Anyways, where you want to be able to say something about the probability of your observables, of your data, without instantiating your whole Bayesian network.
So,
yeah.
Could you say, sort of as a key takeaway, all right, I have this GFlowNet here, and it's sort of, we sort of know how we construct things in terms of, I don't know, maybe use that GFlowNet as an analogy to a basis for a certain space. And then the space that this GFlowNet can create is essentially more descriptive than if I were to just sample from like a hypothesis, a few data points, and then create my maximum likelihood estimator from that. Maybe this is a bit far-fetched, so, but I'm just curious.
I guess what different way to say what I'm trying to say is, I think there are some frameworks that you could instantiate that have some arbitrary latents that you're going to learn. And I think GFlowNets are a good learning objective to find those. But my argument is not necessarily tied to GFlowNets. There might be other methods that do this. It's just that the GFlowNet framework seems to have the energy-based ingredient and the marginalization ingredient, which I think is really important to pull that off.
All right. Yeah. Thank you very much.
Yep.
So can you explain how GFlows are related to causality? Because if every layer has a causal inference, like from the initial state to the final state, right? Then you can easily go back, take a backward path and go and discover the hypothesis, which is from the final state to the initial state, right? So how do you implement causality there?
Well, okay, there's two things here. Sorry, just zooming back to random slide, but that has the structure, right? Like GFlowNets have been applied to causal learning where like the objects you're generating themselves are these Bayesian networks, right? Actually, maybe I should pull this slide. Right, like what the objects that a GFlowNet would sample in this case with the black holes is literally a particular connection and some scalars that are like the strength of the connections in your Bayesian network. So that's one thing. Right? That's kind of just the object space that a GFlowNet is generating. Then what you're asking is like, is there some causal thing going on here? Yes, but that's kind of trivially true because it's just time moving forward in the generative process. So I would refrain from calling that causal because it's kind of, is there causality in an MDP? Yes, just by design, by construction.
But is there any way of bringing causality here?
I mean, so you could interpret, you could choose to instantiate a DAG where the intermediate nodes correspond to some thing, but yeah, that's not something that we've done. So maybe something that's related that might interest you actually is if you're in cyclic GFlowNets.
Like bringing counterfactuals here, from a particular node, you generate a counterfactual node.
I'm not sure exactly what that means, but yeah, sorry, go ahead.
For example, if you say that, okay, so let's say one of the states is that, okay, Kennedy was not killed by Oswald, right? And then you say if Kennedy was not killed by Oswald, somebody else killed him. So something like that. I can't remember.
Yeah, okay. Well, again, I think this is closer to, okay, here's one way to think about it, right? If you think about, again, these final states as explanations of your observation, explanations of your data, maybe in the form of a Bayesian network, then the flow at these intermediate states are marginals, right? They say, I don't know what the mouth and the other eyebrow is, but if I've taken that choice, if I've made this bet that this is a causal connection, then the marginal probability is that much. And that marginal probability might be really low, which says, okay, maybe for what you're trying to do with counterfactuals is, what if I had gone from there to there? You can kind of pre-compute it via just the intermediate state. I don't know if that answers your question really, but yeah. Yeah.
Thank you. So you said that GFlowNets can be applied to the chain of thoughts. But the concept of chain of thoughts, there are no states in there. The states are virtual in there, and actually all the reasoning is just along a sequence that is generated on the way, attached to the previous as the content to generate next words. So do you have here in mind more like tree of thoughts maybe? Or
Sure,
I
yeah.
misunderstand the concept how your approach could be applied to the chain of thoughts.
Okay, so that's great. So one way to understand chain of thoughts right now in LLMs is that it's just generating a sequence, and that sequence has a reward. It's like, is the answer good or not? And that's actually a valid intermediate state, right? The intermediate sequence as it is being generated is just like an intermediate phase here, right? So that's a fine GFLN state. But you're right, actually, that with this GFLnet framework, we don't have to limit ourselves to this autoregressive settings. We could generate any kind of chain of thought structure that we want, as long as we can condition on it properly to then generate the answer. So yeah, does that help?
Yes, thank you.
Yeah, question over there.
Commenting over this, it would be a graph of thoughts, not a chain of thoughts, right?
Yeah, sure.
Right.
You could have a graph of thoughts. I think it's been tried actually, but in like an MLE way, but I don't know if that actually worked. But I'd love to see that done with GFlowNets. Yes.
I'm wondering if GFlowNets will be able to find an error in the hypothesis of the reward. I just wondering if, okay, you say I will generate many diverse solution with high reward, but if I was not able to shape the reward in the right way, I will found two solutions that could be a counterexample one of the other. Was like, okay, I'm in the wrong, I'm doing the reward in the wrong way because I have two good results, but actually are not, one of is the opposite of the other one or something like that.
Okay, I kind of. So I think they did something in that paper where the the model was trying to generate these hypotheses of causal factors between like the size of the gas cloud and then the size of the galaxy and all that stuff, right? And they could actually eliminate some hypotheses because they knew that some causal relationships are impossible because they're unphysical. right? Like the size of the black hole cannot cause the size of the gas cloud. It must be the other way around in particular. So in a way, yes, like you can use, I think, the diversity of all the hypotheses being generated to kind of understand what's going on with your data and how the reward function assesses your data. But I want to say that's like a post hoc analysis step rather than something intrinsic to GFlowNets. But maybe it's something you could automate in some way. I'm not sure.
Thank you.
All right. So no more question. I guess like show of hand of like who would like to look at some Jupyter notebooks versus maybe we can call it a day. There's half an hour left. You can have extra half an hour coffee break. So yeah, please raise your hand if you would like to see a Jupyter notebook. Okay, so people want to. Let's do it. So if you want to follow along, you can navigate to this URL. There's also these two QR codes. So these were Jupyter notebooks that we made for some GFlowNet workshop / big tutorial that we did at Mila a while ago. They're still relevant because it's basically the basics. Explain how to implement in both the action space and the GFlowNets themselves. Cool. Okay, let me close this. And, all right. Okay. Okay. So here I'm opening the session 1. I'm putting the solution set. But if you want to kind of give yourself a challenge, there's like the problem version that has some holes in the code that you're basically invited to fill. Okay, so bunch of imports, some bunch of setup code because we're going to be drawing some smiley faces, but that's kind of unimportant. So, okay. So here are some examples of kind of the state space and in particular just showing that some of it is invalid. So masking will become pretty important. So we're gonna do some smiley faces and the choices are basically 3 choices, right? There's the mouth, the left eyebrow and the right eyebrow. And both all of these pairs are kind of mutually exclusive. So you can't have both happy and sad face. And can't have both left, like up and down eyebrow. So the first thing to do once we've defined the state space is define a reward function. In this case, what we're going to do is say, well, if there's a smile on the face, it's reward of 2. If there's a frown, it's just a reward of 1. Otherwise, reward 0 because it's an invalid face. And important thing to note, of course, is you want a proportion reward that's greater than 0 for terminal states because otherwise you get 0 probability, or if you're working in the log space, of course, you get some infinites. So, okay, now we can plot the state space as I've did in my slides. You see that you start at this initial state, and then your actions kind of lead you to different possible states. And yeah. So here I kind of explain the math that we just did in the tutorial, so hopefully you can skip it. Okay, so now we're going to define the flow model. So the first thing we're going to do is do the flow matching version of things because it's kind of neat conceptually. So what does this model look like, right? We have a very simple state space. There's 6 possible on-off flags for the face, so we're just going to do an MLP with 6 inputs. And then because there's 6 potential actions, right, of like choosing one of these things, then there's going to be 6 actions. And because we predict flows and we want them to be positive, just going to take the exponential here. And yeah, so if you recall for the flow matching loss, we need this sum over parents of these edge flows and the sum over children. So the sum over children is easy because you just take the output of your model, right? It's a vector, 6 dimensions, you can just sum that up. But for your parents, unfortunately, you need to call your model that takes S as an argument. You need to call your model on all the parents. So we're going to need, for this flow matching thing, something that enumerates all the potential parents of a state. And in this case, it's easy. You just kind of remove one feature if it's there or not. And the corresponding action, right, because you need to know what this edge is, the corresponding action is just to add the feature back. Questions so far? All right. So the loss now of, you have 6 incoming flows, 6 outgoing flows, 1 reward. The kind of naive linear scale reward is just sum the incoming flows, sum outgoing flows, minus the reward squared. That's your reward. So, okay, here's the training loop, right? So instantiate your flow model with some number of hidden units, just call Atom because it's a great default optimizer. And here we're going to keep track of the losses and what are the faces that we sampled. And then we're going to do a bunch of episodes. So the initial state, right, as 0 in this case is a kind of empty object, so it doesn't have anything. So in terms of expressing that empty face as a tensor is just going to be all zeros. And then we know for this particular problem that all trajectories are going to be length 3 because there's 3 potential things that you can set. But in the general case, actually, it's something, I think I've talked about it a lot earlier, but if you have variable-sized objects, usually you'll have a stop action, right? So the model might generate a thing and then say, okay, I'm done, give me a reward. So you might have like variable length trajectories, kind of like in reinforcement learning. It's a whole other thing to implement, so we don't have it right now. And okay, so yeah, so we have empty state, right? So this will be this vector of 6 numbers, and to compute the probability, it's the edge flows divided by the sum of edge flows that we have here that defines the categorical distribution, that we then sample, and we get our new state by just adding the feature that we just sampled. And then to compute the loss, as I mentioned, we compute all the parents, turn that into a tensor, feed that to the model, and then we extract the corresponding edge flows of all the parent to child actions, which is what is going on here, to compute the incoming flow of the model. So what you're seeing here is these edge flow predictions, the new state, and now we're going to do this flow matching loss between the incoming flow that we just computed from the parents and the outgoing flow that we just computed from the children. So now we're done with the episode and we loop. Sorry, we're done with the iteration, we loop. And you'll notice that at the end of the trajectory, there is no proper outflow, right? Now the outflow is just a reward. And so we're just going to do that, right? The outflow here is just zeros. All right, so we've finished our trajectory sampling. In like a real code base, you do mini batch sampling, but here we're just going to do one at a time. So this is just kind of doing the optimizer step, right? And if you do that, you'll notice that the loss kind of goes down okay. But this is flow matching, which, as I've mentioned, is not an ideal objective, has lots of bias problems. So, okay, if we look at the sampled faces, remember that I said that the happy faces would have reward 2, sad faces would have reward 1. So in theory, the ideal ratio is 0.66, right? 2/3 of the faces should be happy. Our model got 0.78, not great. But not too far. And we can actually look at the state space that the model has learned. So here you'll see that I've colored the edge flows in proportion, well, with this proportional color scheme, and you'll see that there's a lot of flows going to the happy faces, which is what you'd expect, and that there's some kind of preference over intermediate states, but it's not super strong. We can also check that the partition function estimate is correct. In this case, it is not. Again, flow matching, not a great objective. We can do better. And so, yeah, the total reward should be 12 because there's 4 terminal happy faces and 4 terminal unhappy faces. So yeah, we're pretty far off with this particular model. So next, there's 2 things we can do. First of all, you'll notice that in some of these terminal states, we've generated invalid faces, which is not great. So one common thing that we do in GFlowNet and in just object generation in general is masking the actions, right? If you know that some actions are not legal, you should definitely mask them. There's no point in just letting the model do whatever, unless it's really hard to determine whether an action is valid or not. In general, you should be masking actions. So this is what we're doing here. We're going to compute this Boolean tensor that looks at the state and says, well, if there's already a smile in my state, I'm just going to mask the first 2 actions. If the left eyebrow has been set, I'm going to mask next 2, and so on. And now we can kind of redo the same thing, but with the mask, right? So we're going to say, wherever the actions are invalid, we're just going to predict 0 flow, right? So there's no chance of ever sampling these states, and there's no point for the model to even try to learn that it's 0. We're just going to give it that partial answer, right? So everything else is the same. And now we're doing much better, right? We train the model for longer and it figures out a good solution and gets really low loss. And now you can sample, you can look at the samples, and magically, just with action masking, we've made a terrible objective actually good, and found that the model basically samples the faces, the correct distribution. But because reasons flow matching has some problems, the actual partition function that we get still isn't great. So we're actually overestimating here what the flow is. I'm gonna check here for questions. So the next part of the notebook implements trajectory balance. So there's a little refresher, but essentially, instead of this edge flow, right, we're gonna parameterize the policy directly. And do we have, yeah. And in this particular case, we're gonna parameterize both the forward and backward policy, right? So now our trajectory balance model not only has 6 outputs, but 12, right? So 6 logits for the 6 possible actions forward, 6 for the possible actions backward. And we also have 1 extra parameter, which is the partition function, the log partition function estimate. So here the forward is going to look like this, right? I should probably disable my notifications. Yeah, so the forward takes in the state, grabs some logits, and we split them in 2, one chunk for PF, one chunk for PB. And then we're going to define this trajectory balance loss, just like we did the flow matching loss. As I showed you earlier, this is the log trajectory balance equation. Pretty straightforward. Very important to have log reward, to have the right scale. And we're again going to do action masks for the backward policy. In this case, it's fairly straightforward, right? You can only remove something that's already there. So I'm just checking here if the feature is in the state, in which case the mask for the backward policy is going to be 1, otherwise it's going to be 0. And then do a very similar training loop. So we instantiate the model, the optimizer, we get the initial forward and backward policy tensors, and again, we mask the invalid forward actions. Though here, because we're on a log space, we don't want to multiply by 0. Instead, just put minus big number, which is basically 0 in log space. And now our categoricals has logits as inputs instead of probs. We sample it, just like we did, compute the log prob, add that to our total log probability of PF because we're accumulating over the trajectory. Going to do the same for the backward policy. All right, so we compute the backward policy, compute a categorical with it, and look at the log probability of the backward action, which in our case is the same index than the forward action, so we can just reuse this action. And then again, if we reach the end of the trajectory, the reward is face reward. And once we're done with the trajectory, we add the loss and do a gradient step. Yeah, and then we can analyze the results just like we did previously, right? So the loss function goes down, which you'd expect until it reaches a plateau. And if you look at the estimated log partition function, it's not much better. It kind of neatly grows until it reaches 12, which is what you'd expect. And if you look at the samples, they once again look very good. We're very close to the ideal ratio of 2/3. And yeah, that's an introductory balance. Pausing here for question. All right. So the last part of the notebook showcases the Storch GFN library. Basically, I don't know if I should actually show this, but there's been a number of library developed for GFlowNets. So the kind of generic one that is probably easiest to start to is the Storch GFN library. There's a whole bunch of examples in it. This is one, right? So here we're just rewriting the previous cells, but in terms of that library. So we're defining an environment class. We're defining a way to featureize the states of the environment. We're defining the step. And we're defining the reward. So that defines an environment. And then the training loop is fairly straightforward. Again, you just kind of pass in your model, sample trajectories, and then apply some standard loss on the trajectories. And this is kind of already implemented for you, right? So for example, here, you can just create a standard neural network, standard discrete policy, categoricals, and then call this flow matching loss that's already implemented for you, and then just call this training loop, and everything will be done automatically. Similarly, for trajectory balance, right? Now you need, instead of the flow estimator, you're going to need your forward function, your backward function policy, and then pass in this trajectory balance trainer. And again, simple training loop, everything kind of magically works. And yeah, there's a few other libraries. One that in particular is centered around causal discovery and DAG generation that's implemented in JAX by Tristan Deleur. There's another one that's centered around molecules that I've implemented. which handles graphs, which is its own thing. If you've ever worked with graphs and reinforcement learning, it's a lot of non-trivial stuff going on. And then there's another library by Alex Hernandez Garcia, who worked a lot with crystal generation and these kind of things. And it has really good kind of infrastructure for that exactly, and handling continuous generation really well. And I think, actually, I'm saying all of this, but let me open this up. There should be links to all of these libraries I've just mentioned lying around somewhere in here. Sorry about that. Okay, yeah, there you go. Oh, wait, no. Different things. No. Anyways, if you Google GFlowNet libraries, you'll find them. There's a second notebook that's showing you exactly how to do continuous GFlowNets, simple environments. And once again, at the end of that notebook, there's an example of how to use the TorchGFN library to handle the continuous state spaces, should you need to. So yeah, I think I will stop here because my voice is starting to fail. But yeah, if you have questions, please let me know. And once again, the link to these notebooks is on the gflownet.org website. If you're curious, there's also other materials on that website that can be pretty interesting if you're interested. Yeah, thank you.